Okay. Are you ready to get started?
I'm ready when you guys are.
Okay, well, in that case, let me introduce Jayadev Athrea from the University of Washington. He'll be talking about counting tripods on the torus. Take it away.
Thank you guys so much for this opportunity. I have volunteered to give this talk because I wanted to run by an audience of combinatorialists a set of problems that I think may be of interest to combinatorialists, sort of try and advertise them. And also, I would love any feedback. I'm giving a version of this talk at ICERM next week at a slightly different audience. It's a lattice point counting problems audience. So any feedback you can give would be really appreciated as well. So I wanted to take the pre-seminar, if that's okay with folks. For some of you who I see in this room, this will be a lot of review. I wanted to just share some of the idea of what are the things I count. So I'm not a combinatorialist per se, but I do count things. Mostly I count things which are, there's usually an infinite number of them, but there's a kind of grading on them, and I count them graded by length, which, as Sarah pointed out, is what most combinatorialists do. Sometimes they count things where they're only a finite set of things, and then there's different kinds of problems. But so again, to be very clear for the experts who I see some of, I see Aaron Calderon, I see you, Sam Fairchild, Charles, Heather, Chenshi, Anthony. I see all you guys. So this will be a review for you guys, or even a little bit boring. So feel free to tune out now and come back for from the 410 part. Okay, so let me set up the setting. So I want to just give sort of a very brief overview of counting problems. And I want to state this in a very general, friendly way on surfaces built out of Euclidean polygons. Okay. So what do I mean by a surface built out of Euclidean polygons? Well, I think what I really want to do is I just want to give kind of an atlas of examples to start with. Okay. So let's start by taking a very simple surface built out of a Euclidean polygon. I'm going to take a square, and I'm just going to glue opposite sides by translation. So this is a surface. We can compute its Euler characteristic very easily. Well, we can see this vertex, for instance, gets glued to that vertex because it's red to red, and then it gets glued to this guy over here. All the four collapse to one, so I have one vertex. I have two edges, the red edge and the blue edge, and I have one face, and v minus e plus f then is equal to 0, and that's equal to 2 minus 2 times the genus, so the genus is 1. Of course, we all are very happy to know this guy as a torus. Now, of course, my drawing is a slight lie, so maybe I'll just draw the red curve, the curve with red markings in red and the curve with blue markings in blue. And then this is my intersection point here. Of course, this picture is something of a lie because, when I take this square and I glue opposite sides, it also has a geometry to it, right? The geometry is just the usual good old flat geometry of the square. And then you get closer to the side, you can still put little neighborhoods around here that look like Euclidean space. And of course, the torus that I've drawn here, sitting in sort of 3 space, has some positive curvature, has some negative curvature. Whereas if I glue the opposite sides of this torus, everything is flat. In fact, it's there's quite a lot of work on how, can you put a flat torus in 3 space? The answer is you can't do it smoothly. You can't have a smooth embedding. You can have a C0 embedding. And I think you can actually get pretty close to C1. It looks like corrugated cardboard. So if I wanted to make an accurate version of this picture, it would have to look like corrugated cardboard. Okay. Any questions about that before I state the counting problem that we're going to be interested in on the subject?
And if anyone has a question, you can unmute yourself or post it in the chat.
Great. Okay, so here's the counting problem. This surface has a metric on it. It's a flat metric, and I can talk about geodesics. The flat metric is just the good old Euclidean metric. If you want to think about it, if you like complex analysis, I just finished teaching a course on Riemann surfaces. We could think about putting this thing inside the complex plane. And with this thing with the opposite sides identified, if I think of this point as 1 and this point as I, this is sort of C modulo Z adjoined I, or if you prefer, you can think of it as R2 modulo Z2. Right? That's a perfectly nice way to think about it. And we might say, look, this point 0, let's mark it out as special. Of course, in reality, it's no different from any other point on this thing. It's just an artifact of the way I've drawn it that this point looks like a corner, because all 4 get glued, and this point has this angle of 300. It has 90 plus 90 plus 90 plus 90, 360 degrees. It's not actually different from any other point, but we're going to treat it as such. We're going to mark it, and we're going to call this a marked point. And now we have this metric. We can move around on this surface. So let's follow a geodesic, a local length minimizing path. I don't need to get into a ton of definitions, because I think in this case it's fairly obvious what geodesics are. They're straight Euclidean lines. So maybe I go, maybe I go up a little bit like that, and now I'm down here. So right there, and then maybe I go up like that, and so I should be going, as I go up, I should be going 3 across. Hopefully I did that there too. Yeah, I did. And then I go all the way up there, 3 across. And then if this is 1, so now from here, I'll go sort of 2/3 of the way up, and then I'll come up here and I'll go there, and this line will keep sort of wrapping around the torus in certain ways. This is a slightly complicated one. Maybe I should have used a color for it. Maybe I'll use, so it starts, this is the pink, and it goes like this, and then it continues, and it continues, and it continues. And for instance, something that's not so hard to show is that if you draw a line has slope not in Q, not rational, the line never closes up. It never comes back to where it started. Okay. And much easier, I mean, both are pretty easy. If line has slope in Q, it does. So if you start at the origin and you just go, because of course what you can do is you can of course lift everything to the plane. If my handwriting is getting funky, let me know also. I've been, having the graph paper is useful. So I could lift everything to the plane, or I could just think of having the plane as tiled by infinitely many copies of my kind of fundamental domain for my torus. If you don't know what these words mean, don't worry too much. Hopefully the pictures make it fairly obvious what I'm trying to say. And let's say, if I were to draw some line, and if it has irrational slope, let's say I start at the origin, let's say. So let me mark these corner points. I was using black for that. I continue to go up like this. So let's say if I have a line with irrational slope, that means, not quite a line, but let's say this had slope not in Q, it would never hit another integer point. Therefore, when we look at it down here, it would never come back to 0, because the images of 0 are all these integer points. On the other hand, if I maybe take this guy and it has slope, well, there we go, that has slope in Q, this would wrap around. This would look like this, and then I'd have a piece like this, and then I'd have a piece like this, and then I'd have a piece like that, right? It would wrap around, and we'd come back to where we started. Okay, so here's a question. Here's a counting problem. Count closed geodesics through the point 0 in, let's say, this, either you can think about it as R2 mod Z2 or C mod Z adjoined I. And of course, this is in correspondence with lines of rational slope. And of course, there's infinitely many of these, right? So now the counting problem is, okay, but now I said I wanted to grade it by something. So obviously, the obvious geometric quantity to grade is by length, right? So maybe there's only finitely many of up to a certain length. And so that's the problem we're going to do. We're going to define, let's say, n of r is going to be the number of closed geodesics through 0 in R2 mod Z2 of length less than or equal to r. There's still a little bit of ambiguity here. So let's just go back to this picture, for instance. For instance, what if I took this guy That's a closed trajectory. That's a closed geodesic. So is this one. But this one, in some sense, is just a repeat of that one twice, right? You just run over that same thing twice. So let's say I don't want to count that guy. I only want to count the guys that are actually kind of genuinely new ones. I don't want to count things that involve running over the same ground over and over again. So I'm going to put another word in here, which is say primitive closed geodesics, where primitive means I'm not running over the same thing. Now you can sort of see from this what is the length of these things going to be. So let's say I have something. Oops, sorry. So this guy, for instance, is slope. The rise is, this is slope, I guess, 3/2, right? And that corresponds to sort of the integer vector 2, 3. And notice that GCD of 2, 3 is equal to 1. And here, the problem is, this was 2, 2. A GCD of 2, 2 is 2. GCD of 1, 1 is 1. This is a new one. This 2, 2 going around is just scaling the whole thing. So there's kind of there's a one-to-one correspondence between these integer lattice points with GCD 1 and these closed trajectories I care about. Okay. So in some sense, it's the same thing as the number of, actually maybe I'll just write it now more mathematically, number of mn in Z2 with GCD of mn is equal to 1 and m squared plus n squared less than or equal to r squared. So that's a counting problem. And this counting problem has a really beautiful answer. You know, it's hard to say, you know, what your favorite theorem is, but a couple of years ago, I had the chance to be on the podcast, My Favorite Theorem. And this is what I picked. So let me state the theorem. This is an old theorem. It goes back to, probably goes back to Gauss, maybe. So attribution is a little tricky here. It's old, in other words. Theorem, n of r. So when I write this equivalence, it's going to mean the ratio goes to 1 as r goes to infinity. Okay, so this tilde means, so here means ratio tends to 1 as r tends to infinity. Okay. N of r is, I'm going to write this in kind of a funny way. 6 over pi squared times pi r squared. Okay. The 6 over pi squared is, it's 1 over zeta of 2. It really is 1 over summation 1 over n squared and equals 1 to infinity. This pi r squared is the area of the ball of radius r. And how does one prove this theorem? One proves this theorem by saying, okay, well, it's not, suppose you ask, so this is n of r, suppose you instead ask for the following question, you just wanted to count the number of points in Z2 inside the ball of radius r. Now this is a very, very easy exercise to say this thing is asymptotic to pi r squared, with this equivalence again meaning that the ratio goes to 1. This is the classical Gauss circle problem. And the argument basically is you put around each of your lattice points, you put the square around it, right? So if there's a lattice point, and this is the bathroom tiling thing, right? You know, the number of unit area tiles you need is going to be roughly the area of the room. Of course, you say, well, there's these edges, right? So maybe your circle goes through like this, and maybe this guy is not quite fully in there, or maybe there's another lattice point inside my circle where, you know, or maybe I'm picking up a bit of a square centered at a lattice point outside the circle. You know, how do I account for that? Well, the point is you can do an approximation argument between the circles of radius r minus 1 and r plus 1. And the annulus of between r minus 1 and r plus 1 has area of order smaller than r squared. It has linear order in r, not quadratic order in r. So whatever error you're making is of smaller order. You know, much smaller order, not just it's, you know, r squared and then it's r is the size of the order. So that's if you were to count all lattice points. By the way, there's a bunch of, you know, for those of you who know me, know I also like hyperbolic geometry. If you were to try and run this argument in hyperbolic space, you would fail because the edge of a ball in hyperbolic space has all the volume. In Euclidean space, the hyperbolic space, a ball of radius r grows exponentially in r. So all of the volume is by the edge. Here you're growing polynomially, so the edge of the ball doesn't actually have that much, doesn't give you that much space. Okay. All right. How do you get this 1 over zeta of 2? Well, if you think about it a little bit, so the 1 over zeta of 2 you can sort of think about as this is the probability that a random pair of integers is relatively prime. Here's how maybe you want to kind of think about this. Well, so if you have a prime number, if you have two numbers and you want to know, are they relatively prime or not? In some sense, this is a definition of this probability. You could say take two take two integers in the ball of radius r, or whose pair of integers whose length is less than r, and then what's the probability to have they're relatively prime? This is this kind of thing. But basically, what you can do is you can say, there's this Euler product for zeta of 2, right? The famous Euler product for zeta of 2 is this is 1 minus 1 over 1 minus p to the minus 2. And it's a fun exercise over all p. It's a fun exercise to try and build why this is the heuristic for a pair of integers being primitive. You think about if I have a prime factor showing up in one, so what do you want to avoid? You want to avoid the same prime number showing up in both of their prime factorizations. Try and think about if you have all of their prime factors being, all the prime numbers being kind of equally likely to show up. So if you want it to show up in one and not show up, if it shows up in one, it can't show up in the other. Right? If you sort of write these probabilities down, you'll essentially get this Euler product. I want to leave that as kind of an exercise to build this heuristic. For those of you who've done some analytic number theory, the way you actually prove this 1 over zeta of 2 out here is actually just Mobius inversion. I'll maybe make a quick remark about this also, is that here's one just quick remark is you could look at another version of this counting problem. You could say, let me only look at these guys.
Jayadev?
Yes.
I think your screen is not being updated. At least there seemed to be another person that has my problem. I think you're saying things that I don't see on the screen.
Yes, I am.
Am I the only one?
No, you're absolutely right.
Okay, sorry.
Saying it's mirroring. Let's see. Let's try and do that again. Yeah, so you're not seeing my writing of the Euler product, are you?
I did not.
Yeah, okay. So I'm trying to mirror again, which is, let's say stop mirroring. Okay, let's try screen mirroring again. And now, of course, there we go. Do you see this now?
Yes.
Excellent. Thank you, guys. Appreciate it. Okay, yes, thanks, Graham. Thanks, Farbod. Okay. So now, another way of seeing this is if you look at the counting problem instead, if looking at it in the ball, if you look at it, let's say this is the line y equals x, and this is, let's say, some line r here, x equals r, and you try and count primitive lattice points in there, I claim that this is actually the same thing as summation over n less than or equal to r of the Euler phi function of n. Because for each particular value of x that you get, so if I want to count the integer points in here, so for each particular value of x, the y's that you'll get are the ones that are relatively prime to x and less than or equal to x. So I claim that this is, if you count sort of z2 prim intersect, let me call this is this triangle of r. So if you count z2 prim intersect t of r, that number is equal to this summation. If you apply Mobius inversion to this summation, you'll see that this thing grows like 3 over pi squared times r squared, where is the 3 over pi squared coming from? What's the area of this triangle? The area of T of R is R squared over 2. And so this 3 over pi squared is actually 1/2 times 6 over pi squared. And here, this is the area of the ball. So if you want to think about it, pi is the area of the thing you're dilating, the ball of radius 1. R squared is the coefficient that comes from dilating. Here, 1/2, you could have started with this, which has area 1/2. You dilate it, its area grows with an R squared, and you get this, this result. Now, let me make one more quick remark, is that you could do almost exactly the same thing. You could say, let's look at the number of primitive points in z to the power n intersect, let's say, the ball of radius r and Rn, and this grows like 1 over zeta of n times the volume of the ball of radius r in Rn. Or if you prefer, it's 1 over zeta of n, r to the power of n, volume of the ball of radius 1 in n dimensions. This is also a proof that's not actually terribly hard. Again, this is again thinking about, oh, I want these n guys to be relatively prime. So if I have a prime factor showing up in one of them, there has to be at least one guy of those n, which that prime factor doesn't show up. The Euler product for zeta of n, of course, maybe I shouldn't have used, the Euler product for zeta of n is product 1 minus p to the minus n to the minus 1. And again, it's kind of fun to try and make sense of, you don't want p to show up in all of them, right? That's what we're kind of doing here, is saying, okay, the probability that p shows up in all of them is kind of p to the minus n. It's 1. So if you think about it, okay, let me say a quick sentence about this in the last 6 minutes. Given a random integer, the probability it's divisible by p is like 1 over p, right? Because there's p residue classes that can fall in mod p, right? So it's sort of 1 over p chance. And so the probability that all of them are divisible by p, if you think about them as being independent, is 1 over p to the n. All I need is that not all of them are divisible by p. So that's 1 minus 1 over p to the n. So that's the probability that they're all relatively prime. That's the heuristic. If you do it for n equals 2, you get zeta 2. Did that make sense, what I mumbled there? Okay. All right. So now I want to say briefly some other types of counting problems that I care about. So of course, this is going into n dimensions. What I really love is I love slightly more complicated surfaces glued out of polygons. So for instance, you could take, I'm going to give you 2 examples. This is one that is called a square tiled surface. This is a surface made up of 3 squares where I'm going to draw the gluings as follows. Again, it's Euclidean squares, and I'm going to glue them with by parallel sides or glued by translation. And now, if you actually do v minus e plus f equals f, v or ve and f here, well, it turns out, so let's look at this corner. That's the bottom of red. It's the top of pink. It's the right of green. It's the bottom of pink. It's the left of blue. It's the top of red. It's the right of blue. Hey, all 8 are collapsed to 1. So there's only 1 vertex. There's 4 edges, 4 different colors, and there's only 1 face again. So v minus e plus f is equal to minus 2, which is equal to 2 minus 2 times the genus. So the genus of the surface is 2. It's a genus 2 surface. Another way to see that is to kind of think about gluing opposite sides of this sort of dashed in square. And then you'd get a torus with this kind of dashed hole. And then when you glue the opposite sides of that dashed hole, or 2 sides would be dashed and 2 sides would be solid. One would be this red and one would be this kind of green. And when you glue the opposite sides of this guy, this would also be, I guess, a red. And this would be a green. You'd get another hole. But at this hole, you get the special point, and at the special point you have angle. Well, here you have pi over 2, 3 pi over 2. That gives me a 2 pi. There's a pi and a pi. That gives me a 2 pi, and then there's these 4 pi over 2s left, which give me another 2 pi. This gives me a point with angle 6 pi. So there is, in this case, a genuinely different looking point. And a question you could look at is you could say, oh, well, can I count trajectories connecting that point to itself? So for instance, there's maybe I'll use a different color. Maybe, there's one, but here's another one, for instance, go halfway up there and go across like this, or go halfway up there and go across like this. And perhaps surprisingly, the answer in this case is again quadratic. The growth of these things is again, it grows quadratically in the length. So if you define an analogous n of r, there is a c, so this grows like CR squared. I don't have the c for this guy right off the top of my head. Maybe one of the flat surfaces people in the audience does, I don't know. But I'll say one other thing is that this is a very nice guy, but you could also, very nice genus too, you could also look at one more example I want to do is a genus 0 example, sphere. Let me take a surface that I love very much. Let's see, didn't want to do that. So that's supposed to be an octahedron. Does it kind of look like an octahedron to you guys? There's the 6 vertexes kind of hanging out in the back there. So this is also a surface that you put together using polygons. Except here, if you think about it, the angles, instead of being bigger than 2 pi, are less than 2 pi. They are angles of 4 pi over 3. What's actually happening here is just, since we're not going to need this language for the main talk, I didn't want to spend a ton of time over it. But what we were having in these places, in the torus and on this L shape, is we were taking a surface, you could think about everything as sitting in the plane, and we were saying that dz, the notion of dz, sort of graph paper here, is well defined. Because we're gluing things using translations, and d of z plus c, if you think of z as a complex parameter, is d of z, right? Derivative of a constant is 0. Here, I'm not gluing things using just, if I were to draw the net for this, I would have to glue things using translations and rotations by 2 pi over 3. You can, let's see, I don't have the net for the tetrahedron, dodecahedron off the top of my head, but you can, it's not very hard to draw, and you'll see that gluing it requires gluings of 2 pi over 3. Here, what makes sense is you can have sort of dz quantity cubed makes sense. Because then if you multiply by, if you sort of replace z by e to the 2 pi I over 3z plus a constant, and you take the derivative of this and you cube it, that still is going to give you dz, let's just do the multiplication. That's going to give you the same thing as dz quantity cubed, right? The constant comes out, you cube it, it gets to 1. So this is what's called a cubic differential. And a cubic differential has, and more generally, you can define higher order differentials out of polygons that you glue together with rotations by 2 pi over n. Then you'll have what's called an n differential. And the study of n differentials is what motivates the counting problem that I'm going to talk about in the second half of the talk. Now, what I want to emphasize is you do not need to know what an n differential is to look at the second half of the talk. I'm going to make it completely self-contained. For those of you who know what an n differential is, it'll give you a little bit more context, but you absolutely don't need to know what it is for the second part of the talk. But just keep this example in mind of an octahedron, because here you're going to have some interesting angles. But if you don't like this example, and if you're uncomfortable with points with too much angle, don't worry about it. In the second half of the talk, we're going to spend our life back on the torus, very comfortably on the torus. But the motivation for what I'm going to study comes from studying these kinds of objects. So maybe I'll stop the pre-talk there.
All right, thank you, Jayadev. Let's give a round of applause. There's reaction buttons as well. Okay, so does anyone have any questions?
So this is not a good question, I admit, but what is an n differential?
Oh, great. This is a great question. Okay.
Well, I guess from my point of view, can you say also the fancy way of defining it as well?
Yeah, it's a section of the nth power of the canonical bundle of a curve.
Okay, thank you. But yeah, maybe other people would like to know.
Yeah, no, so absolutely. So if you take so there's so an n differential on a Riemann surface. So if you have a Riemann surface X, you have its canonical bundle, which you can think of as sort of its holomorphic cotangent bundle. And maybe we call this, I guess, K of X is the usual notation.
Yes.
And then you take the nth power of this, that's a nice, so K of X is a line bundle. K to the n is this, so you take this nth power of this bundle and you look at a section of that is an n differential. So it's a section, it's omega 0 of, it's an element of this. So an n differential is something that lives in here. Okay, that's, I think this really reveals the differences in languages, because I think for some people that's an incredibly satisfying and complete definition. Let me state this more flat geometrically. For a flat geometer, what an n differential is it's, and this is not quite a definition, but it's very close. It's a surface formed by gluing Euclidean polygons using rotations by multiples of 2 pi over n and translations. So for example, let me give you an example of a 2 differential on the sphere. I'm also being a little bit sloppy about what I'm being distinguishing between holomorphic and meromorphic. I'm going to mostly be talking about, well, let me give you an example of a holomorphic quadratic. This is called, 2 differentials are also called quadratic differentials. On CP1, this is going to be a picture that looks familiar to all of you. There's a tetrahedron, okay, the regular tetrahedron. It has angles pi at all of these vertices, these 4 vertices, but you can also think about it as a polygon with some gluings. So let me draw these dashed lines in for guidance, but here's a polygon with some gluings of sides, right? That gives you a tetrahedron, and to glue, I have to do translation and rotation, and you can see where the 4 vertices are, right? This is one vertex, and then the other 3 are their own vertex. And you get this, and so why do I call it a 2 differential? Because you can, dz quantity squared is kind of well defined on this object. I mean, dz is not, because I'm multiplying by -1, but dz quantity squared is well defined, because once you square -1, you get back a 1. And an n differential, so I showed you a cubic differential. This is a 3 differential. And this guy, by the way, this has poles. Since you have, basically, if you have deficiency of angles, this is sorry, not 4 pi. This is 4 poles. If you have excess of angle, you have a 0. If you have deficiency of angle, you have a pole. So this is angle of pi. The deficiency of angle you can translate to the order of the pole or the order of the 0 using some basic complex analysis. So yeah, and do you want me to say some more, Farbod?
That was perfect.
Okay.
For me, thank you.
Okay.
Yeah, well, if there are no more questions, let's thank Jayadev again.
Okay.
And the main talk starts at 10 past, so yeah, you have time.